Imagine waking up one morning and finding out that the universe is not just made of particles and forces, but of information. That every collision of atoms, every flicker of light, every thought in your head is part of some vast computation being carried out by reality itself. Now imagine someone stands up in front of a room of computer scientists and says, "If that's true, our computers are hilariously underpowered to even pretend to be the universe." That someone was Richard Feynman, and this is the story of the talk that quietly lit the fuse on quantum computing. Before we dive into the wild idea of simulating the universe with machines, do me a huge favor. Tap like, hit subscribe, and turn on notifications so you don't miss any of these deep dives into the papers that changed science and technology forever. And if you want more videos on the origins of quantum computing or the limits of classical computation, let me know down in the comments. All right, let's step into Feynman's brain. The paper we're exploring is called Simulating Physics with Computers, and it's Feynman doing what he does best, taking a simple-sounding question and following it until it breaks our intuition. His starting point is this: computers, once they are universal, are supposed to be able to imitate any other machine that obeys logical rules. If that's true, can a universal computer imitate nature itself? He doesn't mean approximate a few equations. He means, can we build a computer whose elements interact locally, like little cells in a grid, such that the machine's behavior exactly matches the behavior of a piece of the physical world? If we double the space and the time we want to simulate, we should only need twice as many elements, not an exponentially giant monster. In other words, can the complexity of the computer scale like the space-time volume of the region of reality we're simulating? Right away, there's a twist. Our current physical theories are not written in a way that looks computable. They use continuous space, infinitesimal distances, infinite sums, and fields with infinitely many possible values. A real machine, made of finite stuff, cannot literally handle all that. If you insist the universe can be simulated with a finite machine, you're implicitly accusing our current formulations of physics of being not quite the final story. So Feynman says, okay, let's play. What if space is not continuous, but a lattice, little discrete points? What if time doesn't flow smoothly but jumps in tiny steps? The world would then be like a gigantic cellular automaton, with local rules specifying how each point updates from one tick to the next. Even in this toy universe, we'd have constraints. For instance, if the lattice has a preferred direction built into it, the speed of light might depend slightly on which way you're traveling. That would show up as tiny anisotropies in experiments.
We don't see such strong directional effects, so any lattice has to be subtle enough to hide itself from current experiments. Already, the idea of a digital universe is fighting with precision measurements. Still, in the classical world, things are manageable. Classical physics is local, causal, and reversible. If you know positions and momenta everywhere at some time, or equivalently, positions at two nearby times, you can, at least in principle, compute the future and recover the past. So a classical physical world looks very friendly to a computer simulation. You discretize space and time, replace derivatives with differences, and march forward. But the moment you say the word quantum, everything explodes. In quantum mechanics, you don't get definite predictions for what will happen. You get probabilities. When an experiment is repeated many times, quantum theory tells you how often each outcome occurs. Feynman asks, how do we simulate that? There are two possible strategies. One is to calculate the full probability distribution. For every possible configuration of the system, compute its probability. The other is to build a probabilistic machine that behaves with the same statistics as nature, without ever storing the whole distribution explicitly. The first approach fails spectacularly when you have many particles. Suppose you have r particles in a system, and your space lattice has n possible positions. To describe the full probability distribution, you need a number for each possible arrangement of those r particles on n sites. That's like n to the power of r possibilities. If the number of particles is comparable to the number of sites, that's roughly n to the n. That's not just big, that's laugh-in-your-face big. A finite classical computer cannot store that much information while claiming to only grow linearly with the size of the region it simulates. So the second path is more promising. Don't store all the probabilities. Instead, build a probabilistic computer. Let the machine itself flip coins internally. You feed it an initial configuration, it runs its rules, and if you repeat that many times, the frequency of each outcome should match the frequencies observed in real experiments with the actual physical system. This is how we effectively deal with probabilistic systems in the lab. We don't ask what the probability really is deep inside nature, we just repeat the experiment and count. So, for a probabilistic universe, a probabilistic computer could be a good simulator, if we can design the rules correctly. Feynman then describes what such a local probabilistic computer would look like. Think of space chopped into n points. Each point has a small number of possible states, maybe up to a couple dozen. At every tick of time, the state at a point gets updated based only on its local neighborhood, according to some transition probabilities. If you know the global probability of each configuration at time t, you can compute the probability at time t plus 1 by summing over all possible previous configurations, weighting them by the local transition probabilities. This looks promising, and for classical stochastic systems, like diffusion, random walks, and thermal fluctuations, it works beautifully. But now Feynman turns the same crank for quantum mechanics, and the machine starts to rattle. The full description of a quantum system with R particles is not a simple probability distribution. It's a wave function, a complex valued amplitude assigned to every possible configuration of the particles. The probabilities we observe are the squared magnitudes of these amplitudes, and the amplitudes themselves interfere. When you try to express the evolution of these amplitudes in a form that looks like our probabilistic update rules, you run into something bizarre. To understand the problem more clearly, Feynman uses a different object, the density matrix. Instead of tracking a single coordinate x, the density matrix tracks pairs, x and x prime. It's like knowing both position and shadow position for each point, because quantum states carry phase information and coherence between different possibilities. Even better, he shows that you can transform this into something called a Wigner function, which looks a lot like an ordinary probability distribution over position and momentum. This is where you might be tempted to say, aha, so maybe quantum mechanics is just a funny way of talking about hidden probabilities we could simulate classically. And here is where nature says, nice try. The Wigner function has many of the properties of a true probability distribution. If you want the chance of finding the particle in a region of space, you integrate it over momentum. If you want the chance of a range of momenta, you integrate over space. It lets you do marginalization just like a real probability. But there's a catch. Unlike a real probability, it can go negative. Negative probability. That's not just a weird number, that's a deal breaker for any classical probabilistic simulation. No classical coin flip, no classical dice, no classical random process can directly represent minus 10% chance. Feynman illustrates this even more concretely with the simplest possible quantum system, a two-state system, like a spin 1/2 particle. In a clever construction, you can assign 4 quasi-probabilities to combinations of 2 binary indices. The sums of these quasi-probabilities give you the correct physical probabilities for measuring spin along different axes. Every physically observable probability comes out positive and sensible. But some of the underlying quasi-probabilities themselves are negative. In other words, behind the curtain of quantum measurements, the math is doing something no classical stochastic model can mimic. The universe is secretly allowing minus configurations that cancel plus configurations before we ever see the result. That cancellation is what interference is. The only difference between a classical probabilistic world and the quantum world, Feynman says, seems to be that quantum probabilities sometimes have to be negative, and we simply do not know how to simulate that exactly with a normal probabilistic computer. To see why this matters physically, not just as math voodoo, Feynman walks us into one of the most famous thought experiments in all of quantum theory, the Einstein-Podolsky-Rosen scenario, reframed in terms of photon polarization. Picture this. You have a special atom that can emit 2 photons at the same time in opposite directions. You and a friend stand far apart, each with a polarizing crystal and a detector. Each crystal has an axis angle you can set, and each incoming photon, when it hits the crystal, either emerges as an ordinary ray or an extraordinary ray. Two possible outcomes, call them O and E. Now here's the spooky part. Quantum mechanics predicts that if your crystal and your friend's crystal are aligned at the same angle, your results will be perfectly correlated. Every time you see O, they see O. Every time you see E, they see E. It's as if the photons share some invisible connection. If you rotate one of the crystals by an angle, the correlations don't vanish, but they change. The probability that both observers see the same result turns into a cos-squared function of the angle difference between the two crystals. At a 30-degree difference, quantum mechanics predicts you should match 75% of the time. Now let's ask, can a classical local model reproduce this? Suppose each photon carries with it some hidden instructions specifying what result it will give for each possible angle, like a sheet with O or E written next to 0 degrees, 30 degrees, 60 degrees, and so on. The photons fly apart, each with the same instruction sheet, and when you set your crystal to some angle, the photon just looks up what it's supposed to do. If you and your friend choose the same angle, you will obviously always match, because your photons carry identical instruction sheets. So far, so good. But what happens when your angles differ by 30 degrees? You can play a combinatorial game with these instruction sheets. You ask, given that the outcomes must always be opposite at angles separated by 90 degrees, and given that each angle must be either O or E in a definite way, what is the maximum fraction of times two observers, whose angles differ by 30 degrees, can get matching results? When you work it out, the answer is at most 2/3, or about 66.7%. That's the tightest limit any classical local hidden variable model can achieve, no matter how cleverly we pick the instructions. But experiments and quantum theory say the real world hits 75%, 3/4. That tiny gap between 2/3 and 3/4 is a chasm. In that 9 percentage point difference lives the proof that no local classical probabilistic computer can fully imitate quantum physics. Because any such computer is, at heart, just a fancy hidden variable model with local rules. It cannot reproduce the correlations that arise from quantum entanglement without sneaking in something non-local or non-classical. Feynman loves this. He jokes that he's spent years squeezing the difficulty of quantum mechanics into smaller and smaller corners until it's just one little inequality refusing to budge. But that tiny inequality is enough to wreck an entire worldview. So what are we left with? Option 1. Embrace that the world is fundamentally quantum, with amplitudes and negative quasi-probabilities and non-local correlations, and accept that classical probabilistic computers cannot fully simulate it efficiently. If you want to simulate nature, you need machines that themselves obey quantum rules. Quantum computers. Universal quantum simulators. Option 2. Try to invent some radically new logic, some new conceptual framework in which these weird quasi-probabilities and correlations make classical sense. Feynman openly admits he doesn't see how, but he also admits physicists might be too dull-minded, as he says, to think of truly new kinds of logic. That's partly why he's talking to computer scientists. He hopes that the mindset of computation will shake loose new ideas about reality. He even briefly touches on many worlds, the idea that the wave function, with all its enormous number of components, is simply describing a vast multiverse where every possible configuration actually exists. Our world is just one thread through that cosmic superposition. It's a bold picture, but Feynman is honest. He's not entirely satisfied with it either. Instead, he points back toward a program championed by his friend Ed Fredkin. Try to find a concrete computer model of physics. Not just classical physics, quantum physics. Make the world out of discrete elements. Give them local rules. Make those rules quantum mechanical. And see if we can build a universal quantum simulator that reproduces everything we see in nature without requiring infinite machinery. Because every time we try to discretize a classical field and hit what looks like a paradox, quantum mechanics shows up and says, no, 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 you shouldn't be using classical fields here anyway. You should be thinking in terms of photons, quanta, discrete excitations. The universe saves itself. And that, in a way, is the hopeful message behind this whole talk. The world looks like a monstrous, continuous, infinitely detailed analog machine. But everywhere we really probe deeply, we find discreteness, quanta, bits of action. Feynman is betting that this structure is not a coincidence. It might be the reason the universe is, ultimately, simulatable. But only, he insists, if we embrace its quantum nature.
So where does that leave us today? When you hear about quantum computers promising to crack problems classical computers can't touch, you're hearing the echo of this talk. When people talk about quantum simulators that could model high-temperature superconductors, exotic materials, or even small pieces of quantum field theory, they're trying to build the very machines Feynman daydreamed about. He wasn't writing blueprints for specific hardware. He was laying down a challenge. Stop pretending that classical computers are the end of the story. Nature isn't classical. If you want to play nature's game, you have to use nature's rules. Imagine the full circle. One day, a quantum computer large enough and precise enough to simulate a patch of the universe, including the experimenter, the apparatus, and the photons bouncing around the lab. A computer inside the universe simulating the universe, including itself. That's the kind of recursive, reality-bending idea Feynman was nudging us toward, all the way back in the early 1980s. And it all starts with one deceptively innocent question. Can we simulate physics with computers? If you enjoyed this journey into the origins of quantum computing and the limits of classical simulation, make sure you hit like, subscribe to the channel, and drop a comment telling me which legendary paper you want to see broken down next. Thanks for watching, and I'll see you in the next one.